And what the moment of inertia is essentially the resistance to rotation. Okay, inertia, remember, in and of itself means, right, an object at rest will stay at rest, the object in motion will stay at motion, so it's the resistance to change. Inertia, basically, in and of itself, is resistance to change. But a moment of inertia, or it's called rotational inertia, has to do with the resistance to rotation. And so the way that an object is shaped affects its resistance to rotation. Okay, so that's why all of these equations depend on the shape of the object, right? A rod will resist inertia much differently than a hoop or a sphere or things like that. So there's different equations that they've come up with to allow us to look at the real resistance to rotation based on the shape of our object. Okay, so this is the most basic formula for moment of inertia, and this you'll see is for a hoop type object. Okay? And so you can write this equation down if you want, but you're always going to get this sheet too, so this is kind of an extra equation sheet. This is for a hoop. And so realistically, like when we say hoop, yes, we mean a hoop, but it means really something with an empty center. Okay, so even if I have an object that's on the end of a string, right, and that object is making a circular path, that's the same as a hoop shape, right? If I'm not concerned with the mass of the string or the rod or whatever's holding it, if I'm just concerned about the mass on the end, that would form a hoop type shape on the end. So you have to really think about what we're talking about in terms of the object. Because if you look down like at the uniform rod, right, that would be one in which we pay attention to the mass of the rod itself, right? And it'll tell you that in the problem, like ignore the mass of the rod or incorporate the mass of the rod, things like that. It also depends on the axes of our rotation. So you'll see there's a difference between a rod that goes through the center and a rod that goes through the edge, right, where your axis point is along the edge. So there's a little bit of a difference in your equations there, so you'll get that sheet on all of them. Units for moment of inertia are kilograms times meters squared. So that means your radius has to be in meters, your mass has to be in kilograms, just like normal. Okay. And that will be the case for all of these versions of moment of inertia. It would all be kilograms times meters squared. Okay, all right, I already did that, blah, blah, blah. Okay, two masses are hanging on a bar 4 meters apart. The first object has a mass of 5 kilograms. The second has a mass of 7. The mass of the rod can be ignored. Calculate the moment of inertia when the rod is rotated around the center axis point. Okay, so we're looking at objects hanging on the ends of this 4 meter long, or at least they're 4 meters apart, right? If there's any extra on the edge, like we don't really care about that. We care about the distance they are from the axis point. So it says we're going to be rotating around the center axes, which means our axes would be here, which means the radius of each of these objects would be what? 2 meters, right? Each of them is 2 meters from the center or from the axis point. Okay, because these two objects don't have, don't have equal mass, they're not going to have equal moments of inertia. So we're going to solve them separately and then add those moments of inertia together to get the total of the whole system. Okay, so because they have unequal mass, we have to do them separately. If they had equal mass, right, we could just solve it and multiply it by 2, right, because it's the same thing. But we have unequal mass, so we're going to do them separately here. So when you do them separately, or even when you're doing them together, it doesn't really matter. When you look at this from above, what shape is it going to make as it spins? Right, a circle, but the center or the mass of the rod itself can be ignored, which means we're going to use which equation? The first one, right, that hoop equation, because the masses are distributed along the outside, which makes that hoop shape, right, or that hoop outline. Okay, so when we start looking at, let's say, the 5 kilogram object first, moment of inertia is m times r squared. So our mass is already in kilograms, which gives us 20. If we look at the moment of inertia of our second object, so we're going to add those two together, and we get 48 kilogram times meter squared. Okay, so as long as they are, we can ignore the mass of the rod for both. That gives us the ability to solve with that hoop shape equation. Okay, so you really got to think about where is the mass being distributed and where are we concerned about the mass. Okay? If it would have been 5 kilogram masses on both sides, right, we could have added them or just multiplied it by 2. But either way will work fine. Okay, any questions on that one? Okay. Second part says find the moment of inertia of the system when it rotates about an axis that is 0.5 meters to the left of the 5 kilogram mass. Okay, so I'll kind of draw out again what that looks like. These two objects are still 4 meters apart, but now our axis is here. Okay, so the whole rod is spinning. Oops. Again, if we looked at this from above, right, here's our axis point. If we looked at this from above, there's our axes. Here's our rod. Here's our 5 kilogram and our 7 kilogram mass. Okay, does that make sense? So as they rotate, what do we have? Yeah, 2 different hoops, right? So it's going to be the same type of thing. We're going to be able to solve these separately and then add them together to find the moment of inertia of the whole system. So as you look at it as an overhead view, here's one hoop, right? That's the inner, and then the second hoop, which is the outer mass. Again, we don't care about the excess rod on the end because it said we could ignore the mass of the rod itself. So we're going to solve moment of inertia of the 5 kilogram object first. It's still using that hoop equation. So moment of inertia of our 5 kilogram object is mass times r squared. So how far is our 5 kilogram object from our axes this time? 0.5. That's right. So 0.5 squared. That gives us somewhere 1.3, 1.25, something like that.
Yes.
Okay. 1.25. Okay, the moment of inertia of our 7 kilogram object is mass times r squared. So what's the radius now of our 7 kilogram object? 4.5. 4.5, good. So 101, oops, it's not times 5, it's times 7. Sorry. $141.75. Which gives us a total of 143. Sorry, this was just the 7. The 141 is just the 7. The 1.25 is just the 5. That's right. If there's 2 different objects, yeah, most of the time it's really not even 2 objects, so you'll just have one thing. But see how much different it is? The moment of inertia is so much different for the one that's on the outside of the rod, right? That has much more resistance to change than the one on the inside. So as you get further and further from your radius, you'll see your moment of inertia really increase, right? The closer you are to the radius, right? Remember that feeling when you're on a merry-go-round and you're really close to the center? It doesn't feel like you're really spinning all that much. The further you get from the radius, right, your sensation of spinning gets a lot more intense. And that has to do with your moment of inertia, right? Your resistance to rotation. Okay, this is our new equation now to connect our second law of motion, which is force equals mass times acceleration, and their moment of inertia. And the derivation of that equation is in your book if you'd like to follow along with it. There's not a whole lot of need to do that, but we're going to look at the total torque of our system is equal to our moment of inertia times alpha, which what does alpha mean?
The angular acceleration.
Angular acceleration. So angular acceleration is equal to, angular acceleration times the moment of inertia is equal to the net torque. So this equation works when we have rigid objects around a fixed axis, which we always will. We won't deal with fluids. We won't deal with the moving axis. So this will work for all of our problems. The important thing that you need to notice here, this needs to be the net torque, not the torque of a single object. So it needs to be the overall. Which is what we usually solve for anyway, so that's not anything too different. Okay? Has a radius of 38 centimeters and is given an angular acceleration of 2.67 by applying a force of 0.35 newtons. What's the wheel's moment of inertia? This is going to take a couple different equations because we have our radius 0.38, we have our alpha 2.67, and we have a force. So here's our wheel. Right, we're applying some force of 0.35 newtons on the edge of the wheel, right? Realistically, it doesn't matter if we apply the force there, if we apply the force here, if we apply the force here, right? It's on the edge of the wheel, so it's still going to be perpendicular to our radius, which is what we want, right? What do we need to do if we want to solve for moment of inertia? How can we go about doing that? We have to solve for torque first. Because we don't have the mass, so we can't use I times m times r squared, right? But we do know that torque equals I times alpha, right? And we have alpha. So we need to solve for torque first, which is Fr. Okay, and we already said these two are perpendicular to each other, which is what we want, right? Because it's being applied on the edge of the wheel. It doesn't say it's being applied at an angle, right? So we can assume it's a straight-on type of a force, which means we'll take our perpendicular force, which is 0.35, times our radius, which is 0.38. Okay, so we solved for torque. Then we can set that equal to our moment of inertia times alpha. Really rounds up to 0.050, but that's okay. You could. Mm-hmm. Okay. Okay, so this says the 15 Newton force, which is represented by tension, is applied to a cord wrapped around a pulley. The pulley has a mass of 4 and a radius of 33 centimeters. It's observed to accelerate from rest to reach an angular speed of 30 radians per second in 3 seconds. There's frictional torque. We want to find the moment of inertia. So this has a couple different things that we're going to take care of here. But let's just start by kind of identifying all of our variables and seeing where we can go. So the first thing is our force tension, which is 15 newtons. Our mass is 4. Our radius we need to convert to meters, so it ends up being 0.33. And then it doesn't give us our alpha value, but it gives us our other kinematics values, right? So it says it accelerates from rest, which means angular initial velocity is 0. What's final angular velocity? 30. Time is 3. All these 3s. And then it says that our torque due to friction is 1.10. And we're going to I'll show you kind of how to work that in here in just a second. That's going to apply into our net torque system, right? First thing that we probably want to do is find the torque that we're applying by pulling on this object, right? We're applying torque to pull on this cord, right? We're pulling on it with a force of 15 newtons, and we know the radius, so we're going to find the torque that we are applying. We're going to be able to subtract out our frictional torque, and that would give us our net torque. Does that kind of make sense? Okay, so torque applied is our force, which we are applying straight down, which is perpendicular to our radius, of 15 newtons times our radius, which is 0.33 meters. Okay, does that kind of make sense why we're doing that? Okay. Our overall goal, again, is going to be solving for moment of inertia. And so we'll take this equation to help us solve for moment of inertia. Okay. So the torque by our applied force, I came out with about 4.95. Right? So if we solve now for our net torque, we would say, net equals our applied, so 4.95, and we'll subtract out our friction. Okay, are we on the same page with why we went about doing that? Okay. The reason we can't just solve moment of inertia using mass and radius is because they threw in that frictional torque kind of wrinkle, right? That's the only reason we couldn't just go ahead and solve for that, because there's some friction that's affecting our moment of inertia, okay? So now we're going to take this net torque and we're going to be able to plug it in up here. So 3.85 equals moment of inertia times alpha, which we haven't solved for yet, but we can use our regular kinematics equation to solve for alpha. And so probably you're just going to pick the first one, right? That's the simplest one. So I'll put that in a different color down here. We'd say 30 equals 0 plus alpha times time, right? Gives you a really simple calculation, but alpha comes out to be 10. Okay? So I'm going to plug that moment of inertia in. Plug that alpha into my equation, and my moment of inertia comes out about 0.38